All right, so number one, we start off with the differential equation. On the axis below, sketch a slope field at the 9 points. So identify the location of each order pair, and whatever the x and y values are for that order pair, you're going to enter that into your differential equation, and then you'll get a number, and that number you'll translate into a positive slope, a negative slope, a slope 0, or undefined slope. Undefined slope would mean like 10 over 0 or 8 over 0, 0 in the denominator, and you will leave that blank. Okay, so 1 point at a time. So start off with this left order pair here, -1, 2. So it's -1 minus 3, -4 times 3. So it's -12. That's a really steep slope. -4. Times positive. Okay, any questions with slope fields?
It doesn't have to be exact, right?
Right, as long as you are positive slope, negative slope, 0 slope, or undefined, that's good enough. Okay, part B, find a particular solution. So we're going to work towards trying to separate the variables, but the first thing I like to do is to cross multiply. Leave the parentheses there. They're helping us separate what needs to be separated. Okay, so we immediately notice that we have dy dx's in the right spots. That's good. We don't have to move them anymore. But do we have full separation though? What is still out of place? 2y minus 1. So because the y is attached to all those terms inside the parentheses, we have to move that over to the left side. Don't be afraid to leave your terms in the denominator. I see a lot of students want to make that 2y minus 1 go to the numerator, but leave it in the denominator. Okay, that's where it's supposed to be, and we have rules that can handle variables in the denominator. Okay. Okay, so now we have full separation, right? Y is on the left, X is on the right. It's okay to have Y's in the denominator or variables in the denominator. Okay, I'm going to use as much space as I can, so I'm going to go into the space above from part A. Okay. Okay, what can we do on the left side? Too messy for any one rule to handle, right? So what can we do? Left side, U substitution, right? What could be our U value? Right, the 2y minus 1, right? Entire denominator. Okay, so I'm left with dy equals du over 2. I'm going to reset at the top page here. So left side, I'm kind of treating it independently from the right side here. So I'm just kind of going down the column here. 1 over u, du over 2. I can push that 1/2 out in front. Ends up being 1/2 natural log absolute value of u, and then replace the u back in terms of y. Okay, these are both separate terms. Power rule, right? No U substitution here, right? Both of these are independent. Power rule, power rule. Okay. The calculus is done. We've taken care of the antiderivative. Any questions so far? Okay, we want to get to the y, but right now there's a couple of things that we need to take care of. We want to get that natural log by itself, so we can raise both sides base e, but that 1/2 is getting in the way. What can we do with that 1/2? Yeah, divide both sides by the reciprocal, or divide both sides by 1/2, or multiply both sides by 2, right? So if I distribute the 2 through, I can kind of force that 1/2 to go to the other side. Okay, so 2 times x to the 4th over 4, that's 1/2 x to the 4th. Minus 6x plus c. Okay. Now we have that natural log by itself. We can work towards getting that y by itself. Raise both sides, base e. That will take out that natural log for us. Okay, so now I want to separate that c away from the rest of the problem. But then that operation is going to change, right? That positive sign in the exponent is going to turn into a multiplication down below. E to the c, we can just let that be big C. Drop the absolute value. Now we just want to try to get that y by itself. So add 1, divide by 2. Okay, dividing by 2 is the same thing as multiplying by 1/2. Now 1/2 times c, there's still going to be a c. So here we can let that 1/2 go away. Right? 1/2 times a constant is still going to be a constant. So we can, that 1/2 will just kind of get sucked into that c. So here's our general equation. Okay. The reason why that c is out in front is because when we separated this e to the 1/2 x to the 4th minus 6x plus c, it turns into e to the 1/2 x to the 4th times e to the c. And that e to the c is just a constant. So now it's a constant times this. And we typically like to put the coefficient out in front, so we drag it out in front. If you leave it out in the back, it's okay. It's not wrong. It's just typically this is the way. Yeah.
And then any number you multiply by c.
That's right. Yeah. Okay, so this is general equation. Okay, so order pair 0, 1. Now we can include order pair 0, 1 to help us solve for c. So 0 in for x, 1 in for y. Okay, we know that e to the 0 is just going to be 1. Subtract 1/2 from both sides. So 1 minus 1/2 is 1/2. So c equals 1/2. Once you have your c value, then you can update your equation, replace the c with the numeric value, and now we're done. Okay, part C, find the equation of the tangent line. So tangent line, we need order pair and we need slope. Okay, so order pair, let's go searching. Okay, we do have an order pair here, f of 0 equals 1.
Mr. Gary, the last problem, how did you get it from y equals 1/2 c to y equals
1/2 c. Oh, right, because c is a constant. So 1/2 times a constant is still a constant. So we just let that 1/2 get sucked in. Yeah, any other questions? Guys, I know the algebra is a little messy here, but if you can get to this point where you get that c to come in, the majority of your points is going to be up to this point, right? And same as the AP exam. If you can separate the variables, do the calculus, get that plus c to show up, and then here the effort to try to get that c. If you make a mistake, right? This is relatively. I know it's a lot, right? But this is not as important, right? This is the most important step at this point. If you make a mistake here, the effort is going to count for a good portion of that partial credit. All right. Okay. All right. Find the equation of the tangent line. So order pair 1, 0. Now we also need to find the slope. How do we get to the slope? Yeah, the differential equation. This differential equation is your slope formula. This is your derivative function. So enter 0, 1 in for x and y. 0 in for x, I get 0 minus 3, negative 3. 1 in for y, I get 2 minus 1 is 1. So negative 3 times 1 is negative 3. That's my slope. Okay, everybody good there? So now, point slope form. This is good enough for point slope form, but I'm going to just add that 1 over, get that y by itself to get it ready for my next stage. And that is to approximate f of 0.2, so linear approximation. So how can I move forward with this tangent line that I have? Replace x with 0.2. Yeah. Just insert that 0.2 in for the x, and there we have our linear approximation. So use your calculator. Okay, number 2. We want to try to expand, but that's always our first option. Can we just rely on just expanding and splitting up into individual problems? But we can't do that here, right? Too many terms in the denominator. So our next option is use substitution. Let's explore the portion inside the radical, right? If we think of that as the u value, the derivative should handle that e to the x. I know you're looking at this and saying that, well, the degrees aren't staggered, but this different rule for e to the x, right? It's not power rule. So the derivative for e to the x is e to the x. So we're able to get those to cancel out because the derivatives don't look different. Okay, let's set that denominator up. Right. Anytime you get the parentheses to show up, it makes it easier to spot that u value that we need to target. Right. The derivative for e to the u is e to the u times u prime. Okay. Everybody okay with steps so far? Okay. We want the e to the x to go away, and it does. Pull the 3/2 out in front. Okay, cleans up nicely. But let's be careful here. What rule do we use for 1 over u to the 1/2? Good. Power rule, right? This is not natural log. I know it looks like a natural log because that u in the denominator, but natural log is only for 1 over u to the what power? First, that's right. Okay, so if I see any other exponent, I can't do natural log. I got to force it up to the top and then rely on power rule. So a lot of students get confused between power rule and natural log, and the way you tell difference is you look at that exponent, right? The exponent is a different exponent than 1. Move it up to the top, and then you can do power rule. Okay, add 1 to the exponent. Now, normally we would do plus c, but why do we not do plus c here? Okay, we have bounds, okay? We have bounds. So we're going to clean this up, get everything ready, bring the x back, and then we can work in the bounds. Okay, flip that 1/2 up as 2. Twos cancel out. I'm just left with 3u to the 1/2. Okay, that's my antiderivative. Bring my original variable back. Half bracket. Now the bounds can play a role for us. Okay, upper bound first. Minus. So just make sure that you're spending the time to plug in the 0 as well. A lot of students, they want to do this. They see the 0 and they say, okay, that must mean that everything goes away. Not necessarily. Okay, so spend the time to plug in a 0. Okay, not much we can do. This is a little messy, so we'll just leave it the way it is. Here, this is 2e to the 0. 2e to the 0 is, e to the 0 is 1, right? And 1 times 2 is 2. 2 plus 1 is 3. Okay, you can leave your answer relatively unsimplified, and that's perfectly fine. But we can obviously tell that this 0 is not going to force that to go away, right? There's still some things that are left over, even though partially there are things that did clean up. Okay, any questions? Okay, next page. Guys, I've got the keys attached to the back, so definitely, if you're working ahead or checking your answers, you can definitely do that. Okay, the rise in population of a town is directly proportional. So rise in population, that is the change in population, that's P prime, is directly proportional. We know it's going to be that form of y equals kx to the numbers present. So P prime equals k times P. Or you can say y prime equals k times y. And we know that this differential equation is always just going to turn itself into y equals ce to the kt. But in this case, I guess if I want to use p variable, then it'll be p is equal to ce to the kt. Okay, it's up to you. Whichever variable you want to use, it's going to, anything that looks like a derivative equals a k times the original variable is always going to turn into this, right? And we can go through the steps of separating the variables, but we already know it's going to turn into this, so we can jump directly, skip all the calculus and get to the general equation. Okay, population doubled in 50 years between 1920 and 1970. In 1998, the population was 75,500. What's the population in 1920? Okay, so order pairs. I'd like to gather all my information in order pairs format. I know my independent variable is t. My dependent variable is population. So we don't know the initial population, right? We can treat 1920 as year 0. Okay, so that we don't have to use such large numbers. So we know that year 0, there's some initial population, and we don't know what it is yet. Okay, but we do know that the population doubled in 50 years. So that means 50 years later, what's going to happen to my population? C becomes 2C. And I know that in 1998, the population was 75,000. So 1998, so this is how many years after 1920? 78, right? So we just think of that as year 0. And from there, every year after, we can just count it up. So 78 years after 1920. Okay, so here's our equation. We know that the 0C isn't going to make any progress for us, right? We'll just end up with the same equation. So let's move to 50 equals 2C. We'll insert 2C in for P. We'll insert 50 in for T. Well, the C's go away nicely, so we can kind of focus our attention on getting that K by itself. So our ultimate goal is to work backwards and eventually solve for C. So let's get that K solved for first. Okay, I want to solve for K, but K is stuck in the exponent. What can I do to both sides to bring that exponent down? Natural log, okay. Natural log allows the exponent to freely move, and we have a much easier time working with variables if it's not in the exponent location. Okay, what do you know about natural log of b? This is 1, right? Natural log of b is 1, so we can make that go away. So now we're left with natural log of 2 equals 50k. Divide both sides by 50, and there we have our k value. Okay, we go back to our general equation and we update the k value. And now we're ready for our order pair. Right? So if I insert 78 in for T, 75,000 in for P, I should be able to allow for the one missing variable that I'm looking for, which is that C. I'm sorry, 75,500. I miscopied here. Sorry, my T is 78, right? So I can replace that T with 78. Okay, it looks really messy, but we know that it's just one big number. So we'll enter that in the calculator, divide it over, and then we can just set C by itself. And that's our answer. Okay. Make the calculator do the work for us. Okay, any questions? Okay, number 4, we're going to match differential equation here. I like to gather 4 pieces of information. And the way I like to approach these problems is I want to look for the wrong answers so that I can eliminate them. Okay. So I want to look for, I may not be able to find some of these, but these are the easiest things to look for. Slope zeros, slope undefined. Positive slope. And negative slope. In terms of, can we make some general observations as to where they're located? Okay, do you spot any easily located slope zeros? Not quite, right? These are slightly, they're slightly off, right? So we don't have a perfectly set of slope zeros. So it's possible that there may be slope 0 at x equals 0, but we don't know. These are tick marks that are covering up the slopes segments. So right now we'll kind of leave that blank. It's not conclusive, right? It can go either way. Slope undefined. Do you see any places where there's a blank space where you don't see any slopes or slope segments? Okay. Maybe at y equals 0, but we don't know if that's being covered up. Maybe it's slope zeros that's being covered up, right? So again, anything along the axis, sometimes we're not, it's kind of purposely kind of hiding that information from us. Okay, where do you see positive slopes? Okay, quadrant 1. Quadrant 1 and 4, right? Quadrant 1 and 4, everything here, they all have different variations of positive slope. Okay. Okay, where do you see negative slope? 2 and 3. So I'm going to pick out some order pairs here. Easy order pair here is 1, 1. So I know that if I choose 1, 1, I should be getting a positive slope. So let's see if we can eliminate any ones that are obviously incorrect. Okay, so if I plug 1, 1 into this derivative, am I getting a positive number? No, right? 1 over negative 1, that's obviously not positive. That's conflicting with that, with what we see there. Okay, so that's out. If I plug 1, 1 into the rest of these, looks like these are all positive. So, okay, they're still in play. Okay, quadrant 4. This is 1, negative 1. Also should give me a positive slope. Okay, so 1, negative 1. Is that positive there? Yes. Positive, yes. Okay. Here, if I plug into D, 1 over negative 1 cubed, that's negative, right? Negative is not, so eliminate that one. Still positive, right? So this time we still keep, okay. Negative slopes, quadrant 2. So I'll choose negative 1, 1. That should give me a negative slope, okay. So I plug negative 1 here, negative 1 over 1 squared, that's negative, that's good. Negative 1 squared over 1 squared, that's positive, so that's not consistent with what we know that to be true here. If I plug negative 1, 1, I get a negative slope, right? So I keep that. So right now it's down to B and E. Okay, quadrant 3, negative 1, negative 1. Okay, if I plug negative 1 in for X, negative 1 for Y, I get negative. Okay, This is also negative. So now I'm still down to these two. Okay. Let's see what we can do to decide between these two options here. Okay, x over y squared and y squared over x. One negative one. Oh, we tried that already, right? Okay, 1 negative 1. Maybe, right? We don't know. We don't know if that's a slope 0 or that's undefined slope. Y equals 0, yeah. We don't know. Here, it could be, but also it could be slope 0, but it also could be undefined. The slope 0 could be hidden by the x-axis, right? Okay, so let's try 1 negative 1 here. So 1 over negative 1. Positive. Positive as well, right? Am I getting positive here? 1 negative 1 squared. Okay, so between B and D,
You possibly assume hypothetically because all the marks down x equals 0, that would be 0.
yeah, here, when x equals 0, it could be a slope 0, but it also could be slope undefined. Right, but yeah, you're right. Here, they are showing that for us. Okay, so when x equals 0, my dy dx should be 0. So I plug in 0 here, but if I plug in 0 in here, I'm getting undefined. So yeah, this shawl should be blank if that's true. So B.
Would it be also like okay if you looked at how like I looked in the fourth quadrant and as x increases, then the slope increases. So could you like do it that way?
Yeah, that's true too. Here, as x increases, slope increases as well. So if that's the case, then when x is greater, well, as x is increasing and the y is staying constant, that x is growing. So we can see that as well. Yeah. Okay, so we can use different patterns to kind of help us narrow down our last options here. Okay, number 5. We have sine of u and cosecant of u. These are both u substitution problems. We have a rule for sine, that's one of our older rules, and cosecant, that's one of our newer rules. Okay, but it's always good to kind of, if we understand that these are two separate rules, it's good to kind of separate them. So that we're kind of forcing ourselves to treat them independently. Okay, so this side, my u is pi over 3x. Now, you can also do a little bit of a shortcut here. These are relatively, quote unquote, simple u values. You know that the leftover is always going to be the reciprocal of the derivative. So whatever the derivative is, if you flip it, that's going to be the leftover sitting outside. But I can, go through the full steps to convince us of that. See that the reciprocal is pi over 3, but then it's going to be a 3 over pi that's going to remain. The derivative is 5, but it's going to be the 1/5 that remains. Okay, integral of sine is negative cosine. cosine of u, but bring the u back in play here. Cosecant is one of the newer rules. It's a negative natural log. Cosecant of u plus cotangent of u, and my u is 5x. So 2 negatives becomes positive. That's pretty much all we can do here. Yeah. All right, any questions with 5? Okay, number 6. We see that this is obviously we can't expand. Maybe use substitution, but the u value is not going to quite fit if we just allow for the u value to be that portion inside. And now I'm looking at the gap here. There's a gap of degree 4 and 1. That's a large enough gap where I may have to consider arc trig. So if we want to do arc trig, let's get 2 sets of parentheses to show up inside the radical. Okay. What can I put inside the parentheses so that something squared equals 16x to the 4th?
4x.
4x squared, okay. What can I put inside the parentheses so that something squared is equal to 7? So 7. Okay, so this fits nicely with the arc secant because my u and a, my variable is first, and also I'm seeing that u outside as well. Okay. So let's make our substitutions here. Our u value is the 4x squared, and our a value is root 7. We still have this x to deal with, and we're hoping that the derivative will handle this x for us. Convert everything in terms of u and a. X's go away. It's a good sign. Pull the 3 and 8 out in front. And now it should match perfectly with the rule that we're trying to target. And now we can jump into our rule. All right, 3/8 is going to come first, then the 1 over a, and then the arc secant. And as we get into our rule, we can start replacing a and u with the specific values. Okay, no need to rationalize the denominator. Okay, number 7. If we try to expand, it's not going to quite work. There's a difference of 2 with the denominator being the higher degree, so we need to recognize this as not use substitution, but this is going to be arctangent, right? Arctangent because there's a big gap with the new denominator being the higher degree, and there's no square roots, so it's going to have to be arctangent. Okay, but if we do arctangent, we have to understand that we got to get this denominator in a better form, right? So we got to go to complete the square. Okay, so we add blanks. Okay, what formula goes inside those spaces? B over 2 squared. Our b is 16. 16 over 2 is 8. 8 squared is 64. Okay, this should factor nicely here. Multiplies to be 64, adds to be 16. 8 and 8. And then 67 minus 4, 64 is 3. Okay, let's reset. Get that denominator to be parentheses squared. And then get this 3. How can I represent that 3? Root 3. Okay, denominator sets up nicely. We can now target our u and a value and make our substitutions. Okay. Apply our tangent rule. And coefficient out in front. Okay, so the rule says 7 comes first, and there's 1 over a. Arctangent of u over a plus c. Now look at number 8 here. Number 8, I can't expand too many terms in the denominator, but there's a gap here between the numerator and denominator. It's off by more than 1 degree, but now it's the numerator that has a higher degree. Right? So here, this is not going to be arc trig. This is going to be what? Synthetic division. Okay, so x plus 1, solve for x. So always going to be the opposite sign. Now we got to put in degrees for each term here. So 2 is for x cubed. But what do we have to be careful about with this here? Yeah. Right, we have missing degrees, right? We need placeholders. We're missing degree 2, we're missing degree 1. So 0 for x squared, 0 for x, and -5 for the constant. Okay, we drop the first number below. Number outside the box, we multiply with the divisor. Inside the box, we add, multiply, add, multiply, and add. Okay. We start off with x cubed, so that means every degree is going to drop by 1. So x cubed, we're now going to have x squared to start off our problem. Okay. This is x, this is the constant, and the last term is going to be your remainder. Okay. We haven't solved the problem. We just made it easier for our integral rule to be applied. Okay. first three terms is power rule. The last term is going to be natural log. Okay, normally we do a plus C here, but why not here? Okay, we have bounds, right? So instead of plus C, now we can work in the bounds 1 and 3. Upper bound first. And when you evaluate the bounds, you can leave your answer as one big mess. Okay, you don't have to clean anything up. Same thing on the AP exam. Okay, minus with a big parentheses. Now I can work in my lower bound, 2/3 minus 1. Okay, this is good enough. Okay, number 9, quick adjustment here. If I bring that 3 down in front, because I can expand that 3. And then this is a quick u substitution problem. If I let the u value be natural log of x, I can get the derivative to cancel out this x, and it ends up being 1 over u du.
How do you know when to use natural log? Wait, for number 8, if it's 7 over x plus 1.
Because that's a quick u substitution. If I let the u value be x plus 1, my derivative will be du. So it'll be 7 over u du, which is integral of 1 over u du,
Oh, okay.
which would be natural log.
Let's see. Question on this one. So I got 25,136, and you got like 606. If I just plugged it in my calculator.
Yeah, I'll be looking at your work more than your answer.
Okay.
Okay.
Thank you.
Have a good day.